particle size distribution curve. What is it? How do you build one? And why? What can it tell you about your material, your sample, about the environment it was created in, and why people do that? In this video, we talk about particle size distribution curve, how to build it, the kind of analysis you can do with it, and what it can just tell you just from looking in this curve, what is the main average size distribution of your material. Particle size distribution or grain size distribution, as we discovered from previous videos as well, it's the method to analyze your sample, your sediment. And you're creating this grain size distribution curve to examine the average size of particular grains in this sample. We usually calculated it by weight and then figure out what percentage of it, of the total sample, and you can create the curve. So you can say that particle size distribution is the curve or the graph which illustrates or represents average particle size of your sample. And we're looking at the smallest particle detected till the largest of whatever you have in your sample, and you can see main features of it. Is it composed of particles of a variety of sizes, from very small ones till the big ones? Or it can tell you if it's more or less same size, or there is a couple modes, 3 modes of the grain size distribution, and so on. From previous videos as well, I've emphasized that this is not true grain size distribution. You cannot measure each particular grain separately, and then of course if you do so, which will be a particular number of millions of particles, and you can build your perfect graph. But in reality, we use the average size for particular grain range. So, and it will depend on what type of mesh you have, how detailed you decided to make your curve, and what methods you use. For example, you sieve it dry in the field or in a lab, or using wet sieving, or using the hydrometer, or laser size diffraction methods, and so on. For the methods and what is the grain size itself, see my videos part 1 and 2. So when you build in your graph, you basically recorded the average percentage of this particular size range. It's mean everything that stay on the mesh and didn't fall through, that's where you recorded and you weighted it, or everything that fall through. So you know, for example, 70% of the sample went through the sieve of 1 millimeter, so you know that 70% of your sample less than 1 millimeter in size. Or alternatively, 30% of your sample is larger than 1 millimeter. So that depends which way you're going to look at this. But the principle is the same. And that will depend how you calculate your grain size distribution curve and build it. One of the very important things to remember is that it's average, and remember we talked about the mesh size. Sometimes some grains can fall through and the longer axis would not be recorded, so we have plus minus error. But usually if you have a good set of mesh which are not broken, holes in it, and they've been calibrated, usually it should show you more or less good result. And one of the very important condition for your grain size distribution, it's how repeatable your result. So if you are measuring same sample several times and you within the error and it's repeatable, so show you more or less same grain size distribution, same main parameters, statistical parameters, it means that your sample is of this grain size distribution. If it's not, there's something wrong or with your sample or the method you use, or there's something else not right. So to calculate grain size distribution curve, we take the total mass of the sample and we divided it by the weight of the material that retained on particular mesh or passed through this particular mesh of this on the sieve, and we're plotting each of this sieve mesh percentage on your graph. Its total should be 100%, so you don't lose any material. And often people take 1 kilogram of the sample or 100 grams of the sample, so it's easier mathematically to see the percentage. However, it's not necessary. In the modern world of computer and Excel, you can calculate any percentage simply by putting the formula in the graphs in your Excel and duplicating it, and it will give you the result for all the grain sizes that you are measured, how you can see on this example. You can see example people use set of meshes and they weighted, this represented the number of the mesh and how much it's in size in the millimeters, and then people in the lab measure it precisely the weight of each of the grain that's in this range of the sizes. For diameter bigger than 4.75 millimeters, so everything coarser than 4.75 millimeters, we have 25.87 grams soil retained or material retained sediment. So here probably they were working with some soils. So that's example I took from the internet, and there's a lot of videos you can watch on YouTube, how to actually build this graph, how to specifically calculate it, so you can find information if you need to do it. But it's not very hard. So when you recorded your grams for each of the fraction, here you can see pen, it's everything that less than 0.75 thousandths of the millimeter, which is 75 micron. Everything coarser, it's this 25 gram that recorded on mesh number 4, sieve number 4. So when you build all this, when you put it all in your Excel, then you can calculate a cumulative retained grams on the mesh. And here the total mass of our material was 497.2 grams, so it's half kilogram basically. So here you can see the next graph, cumulative retained grams. So everything coarser, for example, everything coarser than sieve number 10, which is 2 millimeter, it was first two columns 25.87 and 56.3, which is 82.17, and so on. So in the last one you should have the final number of your total sample, which is, in this example, it's 497.2 grams, which is must be about half kilogram. And then you calculate the percentage of the 100. So whatever it's your 25 grams of 497, it will be 5%, then 16%, 43. You can build this graph from mass retained or passing through. So it doesn't matter, it depends how you want to read it, and depends which branch of science you're using this graph for, or if you're a geotechnical or whatever the standard for your report is. Here they're building for the passing. So first they build a percentage column for the mass retained. So everything 5% retained on the mesh number 4, 16 on the mesh number 10 and 4, 43 everything coarser than 20, and so on. And then we calculate the passing percentage, so everything less. So if 5%, a little bit more than 5% of the mass retained on the mesh number 4, first column, so it's obviously 94.7%. So that's how you just calculate for everything, and totally it should be 100, obviously 100%. And then you just plot it on your graph, and here just note that we have coarser grains to the left and finer to the right. This is a geotechnical way of doing it, so usually people study soils for geotechnical reasons, they build it like that. In science we usually look from finer grains till coarser. I usually build it from 0, then 1, then 10, 100, and so on. And we usually interested in the coarser stuff, so you will measure in the field your boulders, gravels, this kind of stuff, and then you will build a total graph as the sum of it. So you might see if in the lab, like they did here, your finer fraction, less than 4.75 millimeter, but everything coarser you will estimate or calculate in the field. But just remember, if you're going to do this, you have to estimate the percentage volume of those coarser fractions, which could be tricky. So when we build it, we just put the points of all, so how many there are, 1, 2, 3, 4, 5, 6 points that you should have, and then you just draw in the line. Well, the Excel program or whatever program you use will draw in the lines and will give you this curve. And here you can see that we have everything less than 0.1 millimeter, not such a big percentage, which is true. Everything less than 0.1, according to the, if you just look on the table, it's less than whatever percent, 9%. So it's kind of more or less correct. And then what we do with this, we will look for some specific properties, specific characteristics of this graph. And that's why we're building it, to understand what is our material meaning. Here, for example, I will look for things like, what is my minimum grain size distribution? I'll always look at this. What is my kind of average 50%? So you see here is a 60%. And where's my 90%? So how big my grain size? So here you can see what kind of span of grain sizes going from 0.1, slightly under, to up to 475. So we don't have much percentage higher, so less than 5%. Bigger, coarser than 4.7 millimeters. So we're kind of working with this range of the material. always repeat, for example, if we have landslide deposit, we have whole variety of grain size. There's boulders that bigger than, I don't know, 5 meters in diameter to the sizes of the nanometer particles. So this amazing span of the particles variety in a landslide deposit, catastrophic rock avalanche material that crushed, fall down big distance, travel a couple kilometers down the valley in a matter of minutes. So sometimes they've been recorded landslide that travel at 1 minute, 1.5 minutes, up to 3, 4, 5, or even 10 kilometers. In this crushing, high environment, breaking comminution in this material created very small particles and very big boulders. And you will kind of try to estimate this range. Or whatever grain size you're looking at, it will show that you have representation of all different sizes. Similar, we notice in, for example, fault gauges. So the area where the two plates, tectonic plates meeting, you have a fault created. Doesn't have to be two plates. Could be just a fault somewhere, quite active fault somewhere in your area. And this material crushed there as well will be similar as a landslide. So you have wide range of the particle size represented there. And then when you have something which involved a lot of water, for example, glacier material, river obviously, beaches, something that constantly washing material and sorting it, similar to sorting material by shaking something, and the coarser grains usually stay on the top and the finer bits with time go to the bottom. So similar in the river of the wave action, they sorting material, so the coarser particles will stay on less distant from the source, and the finer particles will be moved or removed further, and there will be preferential sorting. And if you then analyze this material, or something that been, for example, lake bottom, some sediment supply from the valley into this lake, and of course if you have some kind of catastrophic river flood, you will have a lot of kind of coarse silts and maybe even sands delivered to the lake at the same time. So you will see like a layer of kind of mixed coarser with the finer material. But then when the lake is steady and stable on a sunny day, you can see no waves on the surface, clear water lake. In the middle of the lake, you will have this very well sorted type of material. So it will be settling by the Stokes law, which we talked about in the previous video. Sediment, usually fine silts or clays, settle on the bottom. The settling happening through the months and years. So you will see those layers, and when you analyze them in the lab, you have quite mono-size grain size distribution. So here we have quite representative different varieties, but it's mostly what we can say silts and sands in this example. And then we will build it with trying to understand how much percentage of the gravel we actually have, sands and other fines. And here we look on the curvature and the position of our curve on the graph. First, as I say, this grain size distribution for landslides or something catastrophic, we call it well graded when we have wide range of the material presented. So we have in the clays, everything less than 63 micron, and we have in silts, and we have sands in the gravels presented. Something like in this example we have not so much clay stuff. So there's a wide range of the grain sizes, so we call it well graded. So the gradation of different sizes nicely well represented. So you can find something in finer, in medium size, in the coarser, and the percentage is more or less the same. You can see the percentage on the graph here, more or less the same, equal. So the graph have this kind of about 45 degrees curve, and it kind of tells you about the material grain size distribution, but it's also might tell you some information about where it's come from, as I told you, or what's happened is after it's been deposited. Yeah. Next graph, I will look at something that it's poorly graded, so I don't have a wider range of the grain size distribution presented. For example, on the beach, I will take sample closer to the water and analyze it, and I'll have more or less similar size of the sand. When you build the graph, it will be very steep curve, or maybe not even steep, but it's not representative whole range of the sizes. And when you project your grain size, for example, if I'm looking for a main size represented on this graph on the right, so from 0 point something 2 till 1 millimeter. And I see on the percentage it takes most of the material. So it takes how many? 20, 40, 30, more than 60% of the material will be here of this size. So nothing coarse than 1 mil, nothing less than 0.1, and most of it, 60% of a very particular grain size. So it's very poorly graded. There'll be something from the beach, for example. Often on a river you find material like that in particular areas. It could be also industrially produced material or gravels, or it could be a lot of water involved, settling or sorting. So if you have some environment and you have different layers of the material, and then you have poorly graded and well graded, it tells you that it's different situation happens. So it was a big storm or catastrophic landslide happen, and then you have a period when it's poorly graded, that it's calm environment. Just don't confuse poorly graded, not so many grain size distribution represented, mono grain size, and well graded, a lot of different grain sizes. Sorted, it's different situation. So sorted, it's like on a beach or in a lake, you sort particular grain size distribution by physics of law, in the water, or by wave action or river, preferentially bringing finer material more distant. Here an example on the left graph, you have all these 3 graphs represent poorly graded material. So red one will be something very fine, some kind of fine silts. The black one we talked about, it's very mono size silts as well. And when we look on the blue line, we have 2 grain sizes. So everything between 0.05 till 10 millimeters, basically not existing. Till 2 millimeters, not existing. So it's just a gap. So we have a gap, and then we have very fine grains and very coarse, and it might look something like that in real life. And here we have 2 modes, so 2 grain size distribution mixed together. And again, there will be some type of environment that produced this material. You should think about it, what it could be. Well, first of all, it could be artificially produced by people, industrially, or secondly, it will be something in particular condition and environment that produced this type of grain size distribution. So to also understand our grain size distribution, we can look on the coefficient of uniformity, so how uniform our material. That's kind of mathematically a representation of what I just said. So if you have more or less same size grains, and we have this interesting parameter, we call it D60, D10, D30, or sometimes people use it D10 and D90. It's the diameter of the materials, particles below which 60% amount of particles are finer than this size. So if it's D60, it's 60%. D10 effective size is the particle size of which 10% amount of soil has particles which are finer than this size. 90% majority is bigger than that. So that's what it doesn't mean. So when you look on the graph, you can see D60, for example. Everything you can find your grain size for this material. For example, on this graph, we look on 60%, and it will be about 0.5/6 grain size distribution. Usually programs or Excel will tell you. What does it mean? It's mean that 60% of material, so of this particular size, 0.6, is finer than this size. So 60% of material finer than the size of your bulk material. So that's what it means. Same for 10, 30%, and 90. Laser sizes usually show on 90 and 10. Why we need this? So it's very good mathematical indicator which you can use to calculate kind of mathematical representation of what just I say with this graph. So you can look on the graph and you can more or less for yourself understand it, but then if you calculate it, give you more precise, like more meaningful numbers. Material which more or less same size, like sand on the beach, for example, and you divided your grain size that 60% of finer is and to the 10%, which theoretically must be almost the same. uniformly graded, so same size grains, it should be equal to 1. So when I divided this, it should be 1 because I have and 10% and 60% of my material finer will be same size. So then you can figure out your gradation kind of scale. So if it's bigger than 4, it will be gravels. If it's bigger than 6, it'll be well-graded sands. And it's going to give you indication, you know, what main grain size distribution you have, main particle size in your material you have. But then if you look on this gap graded material, you might be confused because you have n finer bits and coarser and nothing in between. So this coefficient not going to actually truly show you this. So uniformity will show you here it's bigger than 6, but in reality you have n gravels and you have clays, so fine silt. So what should we do? We have this coefficient of curvature, which kind of describe more or less how the curvature behave. And you have a little bit more components, so use N10, ND60, and diameter of 30. And when you calculate it in a way that's represented in this formula, you can end up with a particular number. And then coupled with your coefficient of uniformity, it can give you an indication you have a graded gravels or graded sand or not. But just remember, when you're analyzing your material, I always look on my raw data. So I go into my graphs and look on each and see what is their percentage and grain sizes and weights. Then I looked on my graph and analyze it nicely, and then I do all these calculations if I need to. I do know where's my smallest particles, biggest, how much percentage of finer grains or coarser grains. And it will also depend what scientific question you're asking. For example, if you're looking on a very fine material, you won't be not even interested in the coarser grains. Or opposite, if you just want representative average size of your material, you're not going to be interested in these tails of the finer stuff or coarser stuff. So it very much depends on your scientific questions you're asking. I was looking at landslide material and this physics involved in crushing and creating material. I was looking at a very fine grains, because with the coarser stuff it's kind of more or less understandable. We can find it in the field and we know what could be created. But with the finer grains, it was hard to understand how fine we're going, how actually much of this finer grains created in proportion to the coarser stuff. And that's almost impossible task to calculate. But if you look on finer grains, and because they take so much small space by volume, but such a big number, so 1 millimeter grain diameter in 1 millimeter contain billions of particles of nano size. If you think about physics of creating those grains, because when you're creating grains, you need to apply the forces, well, the physics explain it, you need to apply a lot of forces to create the surface area of the grain. So it's easier to break something in half, and usually it will break in a least kind of surface area because the less energy you include. But if we produce millions and billions of nano-sized particles, how much energy involved in that? In that sense, I was just looking on my tail of finer stuff, so less than 10 micron, 1 micron in size. It's my research question, but you can have different research questions. Just want to know how your wave action, for example, on the beach happens. And I remember from student years, we're going on the beach, we're putting the tape from the wave, from the water edge till the dunes, for example, and whole beach graded in many layers. And then we will take in samples from each of the layer and see the difference in the grain size distribution there. It wasn't significant. So you're just looking at fluctuation from coarser sand to finer sands. And when you analyze it in a particular way, it can tell you something about the wave action. So it will very much depends on your research question. So I hope this helped you to more or less look closer to environment, the curves, and we'll have the last video in this series of the grain size distribution. We will look at actual environments and what type of grain size distribution curvature been created by different scientists from around the world. Of course, it's not done by one person with the same method, so it will be kind of just take whatever exists there and more typical grain size distribution for this environment, and I'll a little bit elaborate why it's so. Meanwhile, subscribe, watch my videos, like and share it, and I'll see you in my next video.